video, we're going to take a look at what's called an exponential function, and we're going to kind of see where it might come from by looking at a couple situations, because there's two kinds of exponential things that can be modeled. Now, the first situation we're going to take a look at is going to be dealing with these alpacas. We're going to pretend that we have a 10-acre farm, and you can typically have about 5 alpacas on an acre and not have to feed them that much, because if you have grass, they'll eat the grass. And so 10 acres can support 50 alpacas. So we're going to start our farm with these 3 lovely alpacas here, and they're going to be females that are bred. And so they're going to have babies in 1 year and all at the same time, and then we're going to breed them. And this is going to be kind of an interesting farm, because not only are we going to breed them, we're going to just pretend that their babies are all females and their babies are all able to have babies the next year, which we know isn't possible, but for nice neat numbers for this situation, that's what's going to happen. And so we're going to create a table. And that table is going to have, our input is going to be time. We're going to start right now, which would be time 0. And then each year we're going to see how many alpacas we have. So let's take a look at that. So we've got our table, and right now it's time 0. And we just bought our 3 alpacas, so our herd size, which is going to be our function h of t, has 3 alpaca in it. Now, next year, 1 year later, all 3 of those have babies, so we now have 6 alpacas. Now, notice that we could have gotten the 6 by just doubling the 3, or it could also be 2 times 3, or we could actually write that as 3 times 2. Now, 1 year later, that's year 2, we have those 6 alpacas are all going to have babies somehow, and we're going to end up with 12. And so that's double the 6, which could be represented as 3 times 2 times 2. Or if we want to use exponents instead, I could have this written as 3 times 2 to the second, which means this one right above it could be 3 times 2 to the first. Now, the next year, year 3, these 12 alpaca will all have babies, and we'll get 24. And that 24 could be 3 times 2 squared times another 2, or we could just say, well, let's make that a 2 cubed instead. Now, if we continue on going on, at year 4, we would have 48, and we would hit our 50 sometime in the 4th to 5th year. And this would be 3 times 2 to the 4th. Notice the pattern. We have exponents here. We have a 4, which matches with year 4. We have a 3 that matches with year 3. We have a 2, which matches with year 2. We have a 1, which matches with year 1. The only spot where we don't necessarily see what's happening is in year 0. But if you remember, anything raised to the 0 power is 1. So I technically could write in a 2 times 0. We don't normally write it there because 2 to the 0 is 1. And so we don't write a 2 to the 0 because it would be 1, and 1 times 3 would just be 3. But I technically could write in times 2 to the 0. And then this 0 would match that right there. You might see a pattern here. The starting amount of alpacas that we had is always this first number here. And then our exponent is always the same as the year in each case. So that gives us a little pattern that might make it so that we could write our equation for h of t. We might be able to say h of t is that starting amount of alpacas times 2, because each year we're doubling, to the t, where t is the number of years since we started our farm. Now, if we just hypothetically want to say that we could have our 50 alpacas anytime during the year, we could go ahead and use this in Desmos and graph it, and then also graph y equals 50 and find our intersection if we would like. That's how we would get our answer. The main point for this part is how do we come up with a function for our herd, which would be this here. And notice that the 3 is the starting point, and then 2 is what we call our growth factor. That's how much it is growing each year, and we're doubling each year. And when you're doubling, you're actually adding 100% on every year. So you can think of that 2 as 100% of what we had the year before, plus another 100% being added on. And that's your growth rate. You always have 100% of what you had before, plus whatever it's growing by. As a decimal, that would be 1 plus 1, which is the 2, which is the growth factor that we have in our equation. Now, let's summarize our equation, and then we'll go to Desmos and see when we hit 50. So, our equation ends up being h of t. 3 is your starting population of your alpacas. It's always going to be your starting amount of whatever you're talking about. And then 2 is your growth factor, and your growth factor will always be raised to whatever your variable is. In this case, it's t for time. So let's go ahead and go to Desmos and see when this function hits 50. Now that we're in Desmos, let's go ahead and type in our function, and we'll do h of t equals, we had 3 times. Now we could do parentheses for multiply, or you can use your keyboard and do times there, and it'll put a dot in there for you. And then 2, and then you use your A to the B button, and then t. Notice Desmos is fine if I use the letters from our equation. And then I wanted to know when this hit 50. So that's going to be when y equals 50. Now, notice I don't see the 50 on there. So I need to make it happen so that I can see that. 50 is your y value, and notice my graph only goes up to 10. If you click the little wrench over here, you can change your y value so it'll go up high enough. Now we need a little room between 50 and the highest y value, so I'm going to go up to 60. And then you will notice I now see my blue horizontal line at 50, and my exponential function, this is a growth function, so it's going up, and you will, as it grows up, it goes to where you can cross right here. And notice we hit 50, which is your y value, at 4.059 years in this case, which wouldn't necessarily in real life make sense, but for the purpose of solving this equation, that's how it makes sense. We will learn how to use logs to solve these a little later, but for right now, you can just do it graphically. Let's take a look at one other situation. In this situation, rather than having a herd of alpacas, we're going to be folding some paper. So I want you to get out a plain piece of paper, and we're going to take a look at folding it. So we're going to start with that paper and have no folds in it. So that means the number of folds in this table is going to be 0. The size of the paper, that's how much of the paper you actually see, is you see one whole piece of paper. So there's going to be a 1 here. Now, we're going to fold the paper, so just like you see in this picture down here, fold your piece of paper, and we're going to record the size of what you see after it's folded in relationship to how many folds we have. So we're going to fold it once. When you fold it once, so that it lines up nicely, you can either fold it hot dog or hamburger if you're familiar with that, and then just leave it folded. You should see half of the paper. So we have half of the paper showing after we've folded it once. Then fold it one more time. So you're going to have 2 folds in it, and keep it folded. Now notice that in this picture here, this one here we folded in the middle, and then I fold it again. So you can see if you unfold it that there's 4 sections, but if it's all folded up, you're going to only see 1/4 of the paper. So our paper size is 1/4. If I were to fold again, so fold here and then fold back up here, so you see 1/4, and then fold that 1/4 in half, keyword is in half there, I would have 3 folds, and I would now have 1/8 of the piece of paper showing. So take a minute and try that. You can pause the video if you'd like for that. Now keep folding this paper. If you fold it forever, these will get smaller and smaller, but think about for a minute, will the paper ever disappear? That's going to bring us to an answer at the very end. So think about that. Even though you're getting smaller and smaller, it's harder and harder to fold the paper. That paper is still there. It doesn't disappear. That's going to be important at the end. But first, let's look at these numbers we put in the table. I had 0 folds, and I saw a half of the paper. I mean, a full-size paper. And then I did 1 fold, and I saw a half. Think about how we could get 1/2 from the 1. Couldn't we take the 1 and multiply by a half? Now, we could, for the 2, we had 2 folds and we got a 1/4. Couldn't that 1/4 equal 1 times 1/2 times 1/2? Because we essentially took this half a piece of paper and cut it in half, which is multiplying it by another half. Now, I could write this just like on the alpaca problem in exponential notation. So I could have this as 1/2 to the second, which means I could have this as 1/2 to the first. You might see a familiar pattern showing. The 1/8, couldn't that be 1 times 1/2 times 1/2 times 1/2? Or in exponential notation, this could be 1/2 to the third power, which means we have a 3 for our number of folds, and our exponent is 3. We have a 2 for our number of folds, and our exponent is 2. We have a 1 for the number of folds, and we have a 1 for my exponent. Now, just like on the alpacas, what about at the 0? Well, couldn't we have this times 1/2 to the 0? And then my exponent here would match my number of folds. That might give you a hint as to what this function is going to be. This pattern that we see in this, because the number 2 says look for a pattern, the pattern that we see in this table is that the growth factor in this case is only 1/2. And so instead of growing, our paper is actually shrinking is what's happening. This is called an exponential decay. The other one had a 2, which is a bigger number than 1. This has a 1/2, which is less than 1, but still bigger than 0. We don't do the negatives because then things get weird. And since this is less than 1 but bigger than 0, what's happening is rather than growing, our paper is getting smaller and it's decaying. Radioactive decay, things like that, will have similar equations that we'll look at later. So if we want a pattern for a function for this, our pattern might be that f of x equals 1, which is the size of the paper, or how much of the paper we saw at the beginning, times 1/2, which is our growth factor, to the x. And that would be our equation. Now, this question right here, if you continue to fold forever, would the paper size in relation to the original paper ever reach 0? And no, that paper would never disappear. So it's never going to reach 0. It'll get smaller and smaller and smaller, but never reach 0. That's going to be important in terms of the graph of this function. So let's take a look at the graph of that function in Desmos after we summarize our function. So our function ended up being that f of x was your starting size of the paper. Notice we had starting size of our herd. Now we have starting size of the paper. That first value is always going to be the starting size. And our growth factor in this case, because it's decaying, is 1/2 to the x. Now let's look at how that graph is different than our graph of our alpaca farm that was growing. So let's take a look at the graph of our paper folding. We had f of x equals, and technically you don't need the 1, but because the 1's the starting amount and we always want the first amount to be a starting amount, I'm going to go ahead and put it in there. And then we're going to have times, and then we're going to do 1/2. When you're doing a fraction, it's always nice to have it in the parentheses. And then the a to the b to get an exponent of an x. Now, let's look at our graph. Notice we said that our graph was never going to, our paper would never actually disappear. This graph is coming down very close to the x-axis, but it is never crossing that x-axis. It's getting closer and closer to it, so close that we can barely see the difference. I can zoom it out, but you can see as I zoom out, it never really actually touches that. So, or zoom in. So it gets very, very close, but never actually touches that. Notice that our growth for our other one went up. Our decay model goes down like this. But we have a horizontal asymptote at y equals 0, which is the x-axis. And if we go ahead and put our alpacas back up there, we had h of t equals 3 times 2 to the t. Notice that if you look at the growth one, it still has that horizontal asymptote at y equals 0, but instead of going down, it's going up. So they're very similar graphs, but one is decaying because it's going down like our paper, and one is growing because it's going up like our alpacas. Let's summarize what we've found today. Exponential functions will always be of this form. You'll have f of t, or you could have, if it was a population growth, you could have a p here. These letters f and t don't necessarily matter. They'd be whatever's in your situation. But the key is that this t would be your exponent on your growth factor. And f of t will always equal the starting amount of whatever you have times your growth factor raised to your variable. One thing to always keep in mind, this growth factor A is always greater than 0. And it is always 1 plus your R, and R is your rate of growth. Now, for our paper folding, our alpacas, we saw that because we were growing by 100%. The R always needs to be as a decimal. So for our alpacas, the A was 1 plus 1 for 100%. Which ended up being 2. Now, what about our paper folding? In that case, our A was 1 plus we were decaying or growing by a negative 50% or negative 1/2. So if your rate of growth in that is that you're going to go down by 1/2 or down by 50%, then it's going to be a negative in your R. So the R would be negative 0.5 because we are going down by 50%, or you could have negative 1/2. And when you calculate that, you end up with 0.5 or 1/2, which was our growth factor in our paper folding. So one thing to keep in mind is that your R is negative if the situation is decreasing or decaying, and it's positive if your situation is increasing or growing. So if A ends up being greater than 1, like in our alpacas it was 2, the function is a growth function. And if A is between 0 and 1, the function is a decay function, as in our paper folding exercise.